Okay, well, yeah, very excited to say that today Jatin will be presenting prompt tuning. So just talking a little bit about, well, there's the link there, of course, on archive. So the power of scale for parameter efficient prompt tuning. I'll leave it over to Jatin to do a full introduction, but yeah, very excited to learn more about it. So yeah, hand over to you, Jatin.
Yeah, sure. Hello everyone. Today I'll be covering a technique called prompt tuning, which was like proposed by some concurrent works in 2021, like by many teams like Google, Stanford. They came up with it independently. So I would be basing my slides using the work done by Google et al. Even though that paper like came out at the last among the bunch, but it tried to unify all these techniques and gave the crucial observation that prompt tuning really becomes effective when we go to the bigger scale, and hence the name of the paper, The Power of Scale for Prompt Tuning. And it was published in EMNLP 2021. I advise everyone to ask as many questions as possible and interrupt me at any point whatsoever. This might be super relevant to the AI developer team, and perhaps at the end we can like discuss how it can be useful to IB in our code generation pipeline and responding pipeline and etc. So cool. So I'll begin. So basically, first before I get started, why do we even want to study prompt tuning? Like the field is moving very fast, right? And there is like new prompting text that's coming up daily. So is it even useful to us, or is it even the state of the art? So actually, the current state of the art on superglue benchmark. I'll explain what superglue is, but it's the standard benchmark to judge large language models. And the current state of that uses the prompt tuning technique. So like before we discuss like we need to first learn the intuition and method behind prompt tuning. Also, the one on the 10th position that you can see by Google is also uses some advanced form of prompt tuning, and that we'll discuss later. So just to give a quick overview of what GLUE is, GLUE stands for General Language Understanding Evaluation, and it's basically a suite of like, I don't know, 8 or 10 natural language tasks, and it benchmarks LLM across like variety of tasks, as you can see in the bottom right. These are like sentence or sentence pair language understanding tasks, NLI tasks, sentiment analysis. So what superglue is just like an improved version of the original glue. There were some mistakes and they just built upon those mistakes, and they corrected those and built this new benchmark of superglue. Uh, and just for reference, like the GPT model is actually at 25th position on superglue.
So sorry,
Okay.
what's the task? Sorry, just quickly. So this is NLP. What
Yeah.
are the, on a high level, what are the tasks and what
Okay.
does it take to do well?
Sure. So basically, let's say the one set of tasks is, let's say, bool q. So bool q is basically Boolean question answer. So it's like, does the triangle have 3 sides? Yes or no? Does fish blink? Yes or no? Something like that. So those are like Boolean questions. There are some like sentence paraphrasing where you like give 2 sentences and you kind of just that if these 2 sentences mean the same thing or not. So a bunch of these tasks.
Is the test set withheld from the people who submit?
Yes,
or is it?
yes.
Okay. Yeah.
It is withheld. It is withheld. Yeah.
Okay. Does it change
so
every
the
year or
only
something? Or
I'm not aware of it. I don't
okay.
think so. It has been changed, but it might. There's a leaderboard version there.
Okay.
So it might indicate that the test set is new or something.
Sure,
but
sure.
we do have labels to train and dev.
Okay. Yeah. Makes sense.
Okay. So I just want to quickly motivate prompt tuning first. So there has been a shift towards modeling NLP tasks as text generation tasks, which means that we can just have a single general model for all our needs. And by changing the prompt, we can just query the model for different tasks. So people have come up with various handcrafted prompts for different tasks. But unfortunately, even using these carefully crafted prompts, we are not able to match the performance of the fine-tuned models. And there are like some people who refer to prompt engineering is like more like art than it's like science. So the main question that this paper tries to answer is, can we learn a good prompt automatically that performs better or on par with the fine-tuned state-of-the-art models? Because if they don't perform on par, it's like it's not useful to us because
So,
we want that.
So just to and I'm jumping in a bit here, but like, so obviously, like when you fine tune something, you have this big generative model, and then you want to train it on a specific task. And what you would then do is take a small data set, you would retrain the entire weights of the entire model slightly towards this new task. And then like in the output, you would basically, and then in the end, you would then be querying this model with whatever questions it is that you care about that you've tried to fine tune around. Well, I guess you'll explain this, but thinking about it more, I don't fully understand how the how you can like optimize in the latent space of the prompt and still be able to pass in arbitrary questions. But I guess we'll get to this.
I'll explain this.
Yeah. Okay.
So So and as you can see on the table on the right, the performance is very sensitive to the prompt that we provide, even though they're semantically being the same thing. So the prompt here is like X is located in Y. This is the original prompt. It gave like precision of 31. Precision is just accuracy. But when we change it slightly, it like changed by a significant margin. And there is no like logical conclusion of why this prompt performs better than the earlier one, even though they semantically mean the same thing. So this is another motivation because there's like the prompt is like very fragile to the evaluation task. So the high level idea of this paper is the paper proposes a technique called prompt tuning, which learns a soft prompt in a continuous space. The meaning of soft and continuous will become clear in the next slide. So, however, unlike discrete text prompts, which were used by the GPT-3 paper, or which is like the current prompt engineering trend, soft prompts are learned through backpropagation. An important thing is that LLM is like fixed during this entire backpropagation. The only thing we optimize are these soft prompts. Also, these learned soft prompts perform on par with the fine-tuned model. So, and the effect of prompt tuning becomes more significant when we increase the model size. So the graph on the right gives a very good high-level summary of the paper, and the trend can be summarized. It's like so this blue curve is actually GPT-3. The top like the orange and the red curves are actually the fine-tuned model. So let's say you pick a question answering task. You just fine-tune our model on this specific task only. So, however, this green curve is actually where you fine-tune only this continuous prompt. And as the one trend is the prompt tuning or the soft prompts perform significantly better than these hard or discrete prompts. The other thing is, as we increase the model size, the gap between prompt tuning and like fine tuning decreases. And when we reach this 11 billion mark, it's actually same as the fine-tuned model performance.
Sorry, I know I just keep cutting in, but this is
sure, no issues.
Like, do you know if they did any experiments where they because obviously now you have this tunable soft prompt, it's basically just like another weight to the network. Basically, it's just some latent optimizable thing. So like, did they do any comparisons to how this compares to like just like fine tuning the first layer of the transform or something? I guess it's all there. Maybe I'll hold questions to the end. Maybe.
It's there.
Sounds good. Okay.
But regarding this point, like that's a very good question, and some concurrent works actually did that, and it didn't yield as much performance as just like doing it in a non-invasive way.
It's interesting.
So
it's still kind of there. It's almost just like the very first weight of the network. Like
exactly, it is kind of like that. I remember reading something like that, but I'll have to check up on it. But this is something I also like thought to myself while preparing these slides, and this is a very valid question.
Super interesting.
So, and the authors of the paper actually says that the language model size is a key ingredient for this prompt tuning to succeed. Okay, and the numbers are like visible on the bottom right. So just the prompt design on a GPT-3 like model, which is of 13 billion size, gives 66.9. Then GPT-3, which is the standard one, gives 3.2. The top two ones only use the discrete prompt strategy. Then if we use prompt tuning on a T5 model by Google, which is a you can consider it like a generator model. It is a generator model actually. So this gives actually 90.5 with just the fraction of parameters optimized. So yeah, cool. Um, okay, so just one small thing before I move on to the actual method. The old way of doing this would be, let's say you're trying to classify the sentiment of some movie review. So let's say the way we normally use this is like we first construct a prompt template. So let's say the prompt template is classify the sentiment among positive or negative, and then this basically means you can feed in any review and we'll give you the answer. So when we prompt using R specifically being witty, touching, and well-paced drama, so then the prompt becomes the following. And then if we ask the model to complete, we hope that it'll reply back with positive generated text, right? Uh, okay, so now we get to the important thing. And if there's any question, please ask. Okay, so uh, a prompt is basically a list of token embeddings that we pass into the language model. So what usually happens is you have a text, you first tokenize that text, then you map each of these token to an embedding, and then this embedding is what you actually pass into the large language model. So in our earlier example, for the prompt, classify the sentiment, blah, blah, blah. The prompt is a list of token embeddings, specifically embedding of classify, embedding of the embedding of sentiment, blah, 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 and then followed by the prompt. So if let's say my R changes, then this list of embeddings would change. So if my prompt R becomes trash movie, then like my prompt would change like accordingly. Is this clear? Like just ignore the things before this, like below this arrow, but is this thing clear before I move ahead? Are there any questions?
Well, actually, hang on. Maybe I'm a little bit. Yeah, well, it's clear for Zaim, but so originally you basically have so I mean, just to rewind a bit. So I know that like there was a period of time where NLP tasks were just like task specific trained. So you would just like train a binary loss on like, is it positive or is it negative or something? And now
Yes.
I've moved to a point where basically you just have this like super general generative text generator model that then like responds to the questions. And now we have a prompt where it's classify the sentiment among positive and negative. So rather than it predicting kind of 1 or 0, you just like embed it into the question. And then R is like just some like template that's going to be the thing that you're going to ask it about, basically. So that's the first thing. So then prompt is a list of token embeddings where so R is then the thing, fine. And then basically we have the words as they are, and then we have these variables added second, and then prompt is a list of tokens embedding for focus trash movie. Yeah, okay. So then prompt now becomes
so I'll move
so the classify the sentiment then is removed. This is kind of where I found it interesting. I assumed that there's free variables and the original question.
Let me explain the free variables first. I think you have a bit of like context. And so basically, okay. Now let's say I come up. So now I'm focusing on the part below the arrow. So now let's say I come up with a new prompt where I take the embedding of let's say trash and the embedding of movie, and then what I do is I prepend 3 free vectors or like free embeddings in that list. So now my prompt actually becomes free vector 1, free vector 2, free vector 3, followed by the review. Similarly, let's say if my R is trash movie, like the other one, the witty, touching, and well-paced drama, then my prompt would now become these 3 free vectors followed by the review.
My question is, does the classify the sentiment among positive and negative, does that remain in the prompt as well or not?
It doesn't. It's not in the prompt. So
I understand. So I understand. So in a way, I understand. Okay. So in a way, like in this context, the idea is that we have this general model, and now the only thing we care about is predicting if it's positive or negative. This is kind of the context. Okay, got it. Yeah. Okay. Sorry, I'm being a bit slow. So we're not trying to train something that's super general. It's always task specific, and in this case, the task is okay.
Sentiment analysis. So now what we do is we freeze the model, we freeze the entire thing, and we only optimize these free vectors or kind of like virtual tokens
using back propagation, keeping the model fixed. Yeah, in my head, we were still trying to fine tune something that's more general than just a positive or negative classifier. Now that that's all we're fine tuning for,
exactly.
Makes total
sense. Basically, these free vectors are the task specific things. And basically, this is it. This is the general idea behind prompt tuning method. Are there any questions before we move ahead? Please feel free if you did not understand anything and ask, because this step is very important. If you understand this, like the paper is like that's it. Like this is the paper. This is the general idea.
Yeah, I would also read. Oh, sorry. I was going to say I'd reiterate there's no silly questions, but I guess Yassi, you're going ahead anyway. So.
Yeah, there's no. I guess the number of free vectors is probably a hyperparameter that you would play with, right?
Correct. Yeah, that's precisely correct. Yeah, it's a hyperparameter, and we'll get on to how these number of free vectors affect your performance at the end. Yeah. Yeah.
Cool. Yeah, I guess there's no other probably.
Should I move ahead then?
I think so. Yeah.
Cool. Okay. So then, so now stating things more formally, our prompt is now a list of embeddings. It's not any English text. It's not any other language text. It's basically some embeddings, and then we prepend these embeddings to our tokenized whatever the variable. So yeah, so basically, let's say for the prompt r equal to trash movie, the prompt now becomes this list: free vector 1, free vector 2, then embedding of trash, embedding a movie. More generally, now my prompt template, instead of being in English, it's a list of embeddings. And as Yasser pointed out correctly, the number of free vectors in the prefix is a hyperparameter, and then this is followed by the embedding of r, for which we want to predict the sentiment for. And this diagram actually summarizes it quite well. So we have a pre-trained model which is frozen the entire time. We don't touch it at all. There's the input text, which is, let's say, trash movie, and then we have these tunable soft prompts that are there. And these free vectors are what we learn using backpropagation. Cool. Okay. So I'll move ahead. So okay. So then once, let's say, assume we have these free vectors already learned. So what we do is we pass this prompt embedding list to our these decoder only LLMs like GPT-3 or whatever, and then we get a output embedding back, and then we project the fourth output embedding, in this case, to my vocabulary space, and then just take a softmax there, and then we'll whatever, and we hope that will predict the it will predict the word negative for this. Is this clear? Okay, cool. Cool. Okay. So then to fine tune these free vectors in the prompt, we can just pass the prompt through the model. When we project the fourth output embedding to the vocabulary, we then take a standard cross entropy loss. Bear in mind, at the setting, the decoder model is like frozen. That is, in the loss computation, the model weights are treated as a constant. So in PyTorch, it's like similar to setting requires grad as false for a tensor. This means the gradients will only be calculated for these two learnable free vectors that we have provided in the prompt. So therefore, only the free vectors are updated in each iteration, and we do not touch the model at all. So in this way, we are able to directly optimize the prompt for a specific task in a continuous space. So is this clear? Shall I move ahead?
I think it's clear.
Cool. Okay. Cool. So then, unlike fine tuning, where we need a different copy of the model for each separate task, what we can have is a general model. And then instead of having different models, we can have these different tuned prompts that are there for each task. So there can be a prompt for a natural question or something like that. And there can be prompt for sentiment classification. So, and then basically we can only learn these task prompts and keep the model fixed, then we are done. Instead of fine tuning each copy of the model specifically for a different task. And once you've learned these free vectors, we are ready to infer on these tasks. So it doesn't involve any prompt engineering. All you have to do is slap prepend three free vectors, learn them, and you're basically done. You don't have to do any like handcrafty things to develop a prompt for a task. Cool. So, okay. So others also show some ablation on prompt length or the number of free vectors. If you just focus on the left graph, what this says is that these curves are basically for different like the different number of for variable number of free vectors. So the blue curves means when we only optimize a single free vector, how does the performance vary on the superglue development set? And as we see, the expected trend would be that as we increase for a given model size, so if we fix the x-axis for a given model size, as we increase the number of free vectors, our performance goes up because now we have a lot more parameters to learn for a given task. But as we see that as we keep increasing these free vectors for a fixed model size, so along the y-axis, can you guys see my mouse moving if possible?
Yeah, I actually can't.
Okay.
But I think we can follow where you're.
Okay.
Yeah, sorry, go ahead.
Yeah, sure. Yeah. So, and then as I was saying that the length of this free vector, the number of these free vectors start mattering less as we increase the model size. So as we increase the model size, the number of free vectors actually they all lead up almost the same performance, and we get like marginal gains as we increase the number of free vectors.
So just to understand, this is the number of free vectors, but the vector dimension is still
so the vector dimension would be the same as what's that of the vocabulary.
Okay, so what would a typical size of that be?
I think so. It's around for a BERT-like model, it's like around 768.
Okay.
Yeah, it's 768.
Because for a second, I was like, "There's no way that one floating point value."
No, it's not. It's not.
So
That's
it's kind of in
what I
terms
said,
of like the free variables in a way. It's like the
Yeah.
1 is like 760, and the 5 is like
Yes,
whatever kind
5
of
cross
4,000
768.
or something. Yeah.
Yeah, exactly,
Okay.
exactly. So
Makes
that's why I
sense.
said it's a list of embeddings
Yeah, got it.
and not a list of float values.
And
Yeah.
I guess the intuition then is that like very, very large foundation models have already baked into them like all of the different tasks to some extent in a much more expressive way, and therefore the key to kind of unlock it doesn't need to be as expressive or something like this.
Exactly. Yes, exactly. That might be one way to explain this.
Yeah.
Okay. So the other ablation that they did was yes. No, go ahead.
Sorry, I joined a bit late, so I hope I didn't miss anything. Yeah, I just have a quick question. How does that compare to fine-tuning the model while freezing? We freeze everything except the heads. Like, how does this approach compare to that on different tasks? So we have like
exactly.
It's exactly the same question I asked actually 20 minutes ago. In a way, I guess the answer comes up later. So
so I can tell you the answer right now. It's basically I'm not sure on this, but I think they did some ablation because where they actually try to fine tune different parts of the model, and they did not perform as well as just keeping everything at the input and then doing everything in the input space and then not touching the model at all. One reason that they explain is that because once you do it at the input stage, then as you move through the attention layers, they might be able to use that information better as compared to when you only do it at the head. So that's, I think, one explanation they gave, but I'm still not sure about this. But that's one reason that they give is that because you do it at the input, then it has much more representation power in a way, so that it can in the later stages of the layers, it can use that information well. And but I'm still not sure what's the exact reason for this performing so well.
I think that makes sense. There's quite often the case where when you do like latent variables and stuff, that having them early in the network is better because, as you say, just the expressive power becomes much stronger because it can compound through the network. So I guess that does make sense.
Yeah. Okay. Cool. So I'll now move on to the right diagram that is there. So what this ablation is basically each. So I'll just explain the blue curve first. So the blue curve is basically where they initialize these three vectors randomly. So it's randomly initialized, and as we increase the model size, the initialization of these, like this random initialization, perform as well. Now I'll explain the orange curve. What sampled vocabulary means is that they initialize these free vectors randomly using an embedding that was already learned in the vocabulary. So this word can be anything. It can be, let's say, good, or it can be anything like a pillow. So basically, they initialize the free vectors using some learned vocabulary token. Does that make sense? But they picked it randomly. Okay. And the third thing that they do is class label. So instead of assigning any word from the vocabulary randomly, what they did is that they, let's say there are like 5 free vectors. So 2 of them, they actually assigned the embedding of, since we don't, let's say, sentiment analysis. So they assigned one free vector the embedding of, let's say, positive, and the other free vector the embedding of negative. The position of them doesn't really matter. And the important thing is, as they just initialize these free vectors using one of the class labels that we actually want to predict. So let's say positive or negative. There might be other classes as well, but in sentiment they're like just 2. So yeah, just 2. And then like as we see, like for, let's say, a model size of around like 1 billion, so the center thing, we see that when you initialize it using a class label, it performs better than if you just initialize it using some random words in the vocabulary, and then followed by if you initialize it randomly. But the interesting thing is, all these 3 things start mattering less as you increase the model size. It doesn't matter how you initialize them even. It's always good to initialize it using the class labels if you already have it. But then if it, let's say, some natural language generation task where you don't actually have the class labels, or some translation task where there's no label that exists, it might be better that you just initialize it using vocabulary, or even if you don't have that, random initialization might work just as well.
I wonder what their like training time and convergence is like.
That's the next slide.
I was going to say, because I'm sure it gets there in the limit,
Yeah.
but probably it's a lot slower. Also, I'm a bit skeptical about the random uniform graph. I feel like they maybe didn't do enough like perturbations.
Probably, but I think though, like there's like this standard deviation that you can see, like it's pretty high on these smaller model sizes as
Yeah, but
compared to
not as high compared to the crazy thing. I feel
yeah,
like
yeah, it is. Yeah,
I don't know. I'm a little bit skeptical about that. I feel like that isn't probably the true trend, but
makes sense. Makes sense. It might be just it might be just coincidence. Yeah, that perform well, but yeah.
Maybe their error bars just aren't quite correct or something, because I think
maybe
maybe it is, but yeah, I was going to say something else, but I forgot now. But yes, I had a question.
Yeah.
Yeah, but you already asked it. What it was about the color. Like,
okay, there we go.
Thanks for asking, I guess.
Yeah.
I had something else, but if it comes up later, I'll ask it later.
Cool.
Oh no, that was it. No, I was just going to say I think it's 10 billion, 10 to the power of 10, right?
Yeah, 10 to the. Sorry, what?
Because you said 1 billion up to the limit of
1
billion.
billion is like 10 to the power 9, and then 10 billion is.
Yeah. Cool.
So, like the summary is trend for initialization of free vector is that it is sensitive to initialization in smaller model sizes. However, as we increase model size, initialization of the prompt does not matter. And this is where I go back to the title of the paper, the power of scale and prompt tuning. So as you increase the scale, everything starts mattering less. Okay. Okay, so now I'll come on to the compute requirements. So basically, let's say we are fine-tuning, let's say 5 free vectors for a model which is, let's say, T5XXL. It's a encoder-decoder model by Google, and it has like 11 billion parameters. And let's say we are in the paper, they mostly use free vectors as 5. So we are basically, and each embedding is, I think, around like 4K, 4096 size. So then basically we are optimizing 5 into 4096 parameters, which is 20K. Now compare this to like fine-tuning 11 billion parameters. So this is like 2, 5, 6 orders of magnitude less. And the resources they use is 16 TPU V3 chips, I think, for the largest, for all the experiments, which is I read some tweet which is almost equivalent to 8 V100s. However, I'm like still skeptical where is the memory requirement going up, because let's say 11 billion model, even let's say if they do it in float 16, that's like 22 GBs of space of just to store the model. But when you do the predictions, you also need the activations. So, but the activations I don't think would be a lot. Yeah, so I'm not sure, but then maybe these V3 chips are not equivalent to these V100 NVIDIA graphics cards. Maybe the memory requirement might be low. Maybe just they need more compute power to do it faster, something like that. I don't know. So
you also still need to do the entire backprop, don't you? I'm just thinking like in terms of what this actually means in terms of the algorithm, you still need to go right from the outputs through this 11 billion parameter thing, which means you need all of this in memory in some way, and then you just update the final ones. Or am I being...
So actually...
Oh no, it's frozen. No, you don't. It's frozen.
Yeah, exactly.
Yeah, no, yeah.
You only need the gradients of the activation, and you only need the gradients of the free vectors that are there.
Yeah.
Because the way like this chain rule works is that you don't go to the parameters. You will stay at the activation layer.
Yeah.
And so what they do is like then they do a grid search over the best hyperparameters for a fixed task. So the training time, the paper only reports the training time for a data set called bool q, which is part of the superglue suite of 8 tasks. And this data set has around like 10K training points, 3K validation for the dev, and 3K tests that is there on the server. And we see that the 11 billion model takes just under an hour to converge, assuming the prompt length is 20. And as we increase the model size, the prompt length, the time naturally increases. I'm still not sure what's the whole fine-tuning training time for T5, but I think it would be in days. I think so. I'm still not sure. I need to check up on it, but it would be definitely in days at least. So in terms of like the numbers on DevSet, like the GPT, like the discrete prompt GPT-5, GPT 175 billion attains 73.2. A fine-tuned T5 model, which might take like days or like magnitude of more hours, achieves around 91, but the fine-tuned, the prompt-tuned 11 billion model attains around 90.5. So like basically this table.
So sorry, quickly, the top left one, starting there. So sorry, what do you think these numbers are? So we've seen the graph before, up to that like cement everything. The top left, sorry, what are these 9,427?
So these are the so the paper reports the training time for this bool q specific data set only. They don't report it for the other data sets that are there in superglue benchmark. So for this specific data set, the time it takes to train is around an hour for the biggest T5 model that is there.
Around an hour?
That's it, yeah.
So sorry, is that 9,427 seconds then? I'm confused a bit. Sorry,
No,
the top left. The top left. No, because that's 3,000.
These are the train points. Yeah,
the number
these
of
are number of
examples.
examples. Yeah,
okay,
exactly.
and then test, and then like the validation set and stuff.
Yeah.
So, okay, sorry. Yeah. Okay.
Yeah.
Okay, and then the middle one is just showing the scores, basically the accuracy. So like percentage out of 100.
Exactly.
And these are the different data sets it was trained on and how well it does.
And then you take the average.
Dev.
So these all
is superglue dev like the best one? Sorry, I'm a bit confused what superglue dev means.
Okay, the superglue dev is basically the average of these points mostly. Like these all data sets are part of superglue, and when you report the performance superglue, it's actually the average of all these scores.
Okay, and then the top right is just where you think it's training time in days, basically.
Though this is training, this is like minutes followed by seconds. So the first one, 3:17 is 3 minutes, 17 seconds.
And that's the time it takes to...
Yeah, just 3 minutes. To train the biggest, so to train, I think large is around, I don't know, 3 billion parameters. To train a prompt length of 1. And then, so basically for the biggest T5 model, it takes just 21 minutes to train, just when we have like the free vector. There's one.
Got it. Yeah, okay. Makes sense.
Yeah.
Okay.
Okay, and just for reference, the state of the art on Superglue, which is the Vega V2 model, attains around 91.3, which also uses which uses prompt tuning as well as some knowledge distillation to achieve like the state of the art there, and that's only a 6 billion model only. So like this is like very relevant, and it's actually being used to achieve like to achieve state of the art scores basically. Uh, okay, okay. So another thing that the authors evaluate the performance on prompt tuning versus fine tuning is on out of distribution data sets. So like in this table, basically we learn a prompt on one paraphrase detection data set and then test it on some other paraphrase detection task. So basically MRPC is Microsoft Research Paraphrase Corpus. And so what we do is like we first we first prompt tune as well as fine tune the T5 model on this data set, and there it again the prompt tuning attains like 76.3 or 73.1. So the fine tuning attains 71.3, the prompt tuning attains 76.3. Oh yeah, sorry, I'm getting confused, just give me a second. Oh yeah, sorry, my bad. Sorry, my bad. It's okay. So actually, you train it on QQP first. I'm explaining the first row that is there. You train it on, let's say, a data set which was taken from Quora, and then you test it on a data set which came from like the Microsoft Research Paraphrase Corpus. And then the accuracy that you see is on MRPC, even though the model was trained on QQP. Does that make sense?
So it seems like there's some kind of regularization effect happening that means that it does better. And this is accuracy on the validation set or the test set, obviously.
This is the accuracy on the validation set of the MRPC data set. So
no, of course. It's just weird. Like maybe what's happening in the model tuning is it's like overfitting a bit or something. Because obviously, generally speaking, you expect that the more expressive training optimization. It'd be interesting to see which of them does better on the training set, because I would suspect that the model tuning does better on the training set.
Exactly, it does. It would do. They haven't reported that, but I think the fine tuning one, in my opinion, also should do better on the training set. And the reason for this behavior, the author says that there's a thing called catastrophic forgetting, where the LLM start forgetting when they are fine tuned on a downstream task. So by freezing the core language model parameters, prompt tuning prevents the model from modifying its general understanding of the language or the tasks that's been trained on.
Yeah, it's like a form of regularization, because whenever you train on a really small data set, you have like huge risk of overfitting.
Exactly.
And I guess probably some other regularization might alleviate this a bit, but I guess because you've learned all this stuff and you're kind of saying you can't forget this, you can just learn some new kind of key to like, or some new like expressive vector to kind of unlock the power of this LLM, and that's just like prevents the catastrophic forgetting.
So it's kind of like in a way we are like modulating its behavior using a prompt, where we kind of like that.
Yeah, makes sense.
So okay, is this clear? Are there any questions on these?
I think it's all good.
Okay, cool. Cool. Then I like then they do some like some bunch of like bunch of ways to in order to improve its performance further. So what you can actually do is like instead of just learning a single prompt, you can basically learn 3 sets of prompts for the same task, and then you can basically ensemble their prediction. So it's like kind of an efficient way of ensembling, since we're just using one copy of the model. And we can actually pass all 3 prompts in a single batch because these are just prompts. So, and then we can just select the answer based on majority voting. So, yeah.
And sorry, do they compare that to just the case of multiplying the size by 3?
So, you know what I mean? Technically you can't, because, okay. I think they did not. They did not compare it with when you actually ensemble the fine-tuned model. They didn't.
And also, is
Right.
this that they train each in the ensemble independently and then just aggregate them, or is the entire ensemble back to back
So,
end-to-end
there-
trained?
so like to abstract it out, technically they are trained independently, but because you can actually pass them in the batch and actually train them concurrently. I mean, the
Yeah,
model
no,
doesn't.
I know what you mean. But I meant the
Yeah, yeah.
gradients, just the gradients. So
Yes,
they're
yes,
trained in the
yes.
batch, obviously, but the gradients they're trained independently.
Exactly. Yeah, they are independent.
Interesting.
Yeah.
Interesting that they don't. That's well. I mean, it's kind of like Bayesian networks and stuff, and the fact that
Yeah,
you
it's
can-
exactly. Yeah.
So I
It's
guess-
kind of like approximate Bayesian kind of a way. Yeah, but yeah.
Yeah, makes sense. But yeah, it'd be interesting to know if that does better or worse, because you're kind of like multiplying the size by 3 in a way, like of
But
your
then
latent
those.
space.
Yeah, exactly. But those that even if you multiply it by 3, compare it with 3 into 11 billion.
Yeah, no, of course. But my point is
Yeah.
just it'd be interesting.
Yeah,
It'd be an
yeah.
interesting comparison to see like this ensemble with 3 that are like independently trained versus
Yeah.
multiplying the size of the latent space by 3 and training it all as one. Like what the difference there is, because there's kind of more expressive power in the one where you just multiply it by 3, because you
Yeah.
kind of have end-to-end training, but and they can like learn to like each focus on different areas, whereas in this case they're all trying to focus on the same thing, and you're just leveraging the random initialization to like actually get some like stochasticity modeled. But I would think that something like 3 would probably perform better, I would assume.
It would, but then how much the gap would be, that's the interesting thing. Like maybe if we are just like getting like 0.5 increase, then it's not worth putting effort into that. We can just improve. Yeah.
And also I guess the memory requirements are a bit bigger, maybe
a lot bigger.
For times link by 3, I guess.
Yes, exactly.
Yeah, it makes sense. Okay.
Okay, I think Yasa has a question. If all the problems are trained within the conversation very similar, and does they train on different data, it still come from the same? So I think the initialization here would matter because as we know, like SGD works on converging on a local minima. So there can be like different local minimas for the same task. So that might end up training them to different embeddings. There might be a good chance that they actually end up in getting like they converge to the same thing, but that's what we hope they do not do. So that's why that's why we do ensembling, that we expect there are like different solutions to in the parameter space to the given training set, and that's when it's an ensemble.
It's also a very good way of modeling noise as well, in the uncertainty of a network, because basically if the network's really confident, then regardless of the initialization, you'd expect all of them to agree. Whereas if it's not clear, then you'd expect them all to disagree. So it's kind of like Bayesian networks, how you model kind of uncertainty in networks and stuff. Yeah.
Exactly. Basically, instead of like in Bayesian where you integrate all the parameters, you just like average it up, the predictions of you average out the predictions instead of like predicting for each and every model that exists, something like that. So it's a approximation to Bayesian models. This ensembling thing, okay, cool. Okay. So this is interesting. So what the authors did is that looked at the interpretability of these free vectors. Like, do the learned free vectors have some semantic meaning? Like, we have learned these, but might as well look at them. Like, like if I looked at, let's say, pick the random free vector that was learned, and I looked at a word embedding in the vocabulary, which was like the closest to this. So how would that free vectors look like? Like, what would that word be actually? So the authors observe that for a given like learned prompt token, the top 5 nearest neighbors form a very tight semantic cluster. So let's say the top 5 neighbors of a let's say a token then would be like entirely, completely, totally, altogether, 100%, something like this. They also report that on BoolQ dataset, 20% of the questions are from science and technology domains, and some free vectors have their nearest neighbors at science, technology, engineering. So it's kind of like the model is keeping a memory of what kind of questions that might appear, and then it's like kind of learning those in those free vectors that are there. And in longer prompts, they find that several free vectors actually have the same nearest neighbor, which means that we have like more number of parameters than we actually need. So we have extra capacity. So yeah, but that's that's mostly the issue that they give. Yeah. Cool. Okay, then I'll move on to some like future work that have been done. I think the size of the model even does not matter. They like come up with new techniques where like the smaller model also perform on par. But there was like this one interesting work that was there. So basically what you do is, uh, let's say there are thousands of sentiment analysis classification tasks, right? So instead of training a prompt for each of those data sets, what they do is like they maybe combine a lot of big data sets or maybe in an unsupervised way. Can we can we pre-train a prompt? So can we pre-train these free vectors? And then depending on your task, there would be a suite of prompts that you can take. Let's say you're doing sentiment analysis. I just take those already pre-trained vectors, then fine tune those. So it's kind of like prompt transfer learning in a way. So this is what is explored in the paper called Spot, which is again by Google. And actually it's from the same authors as well, of this parameter efficient fine tuning paper, and this achieves the 10th position on Superglue benchmark. So doing prompt tuning alone would not like fetch you maybe the state of art results, but when you have like a more general prompt which has been trained on a lot of examples, then you can maybe like transfer its knowledge to your specific task.
You could also apply meta learning here, I guess, where you do like model agnostic meta learning or reptile or something to actually like
Probably.
to meta learn a really good initialization of the prompt, which then with kind of a one-shot learning or few-shot learning, you could then like very quickly optimize to a new task. That could be quite a good way of like getting a really general pre-training of the prompt or something. I mean, I guess this works doing that already probably, but
yeah, probably.
Yeah,
cool.
no,
And also the state of data approach that I talked about, Vega V2, they also use this spot method in one of the tasks to achieve. So basically, I think as far as I remember, on the 7 tasks, they do some sort of knowledge distillation plus fine tuning. That's like complete fine tuning, which takes a lot of time. But on one specific task where there are a lot of like, there's like very less training points, that's where they employ this spot method, where they only prompt tune, because otherwise the model would like quickly overfit to that small training set. So in that specific task, they use this prompt tuning thing. But for the other thing, for the other 7 tasks, I think they develop some novel pre-training based on knowledge distillation. Yeah, I'm not like but I'm not fully aware of the method, but I use some sort of knowledge distillation, and they change the pre-training task. Yeah, but they achieve all this using just a 7 billion model. And the important thing is, like, for each of the tasks, the 7 billion model is separate. So they're like 8 different 7 billion models, but in the last model where there's like in the last task where there's less training points, they might just pick any of these 7 models. Yeah, because they're only tuning the prompt, something like that. Yeah. Cool. So yeah, that was it from my side. I hope you guys like was able to take away something from this. And if there are any questions, and especially from the AI developer team, if in any way we can use this, so please shoot your questions. Yeah.
Amazing. Well, first of all, yeah, thanks a lot, Jatin. That was super interesting and helpful.
Yeah,
well,
it's the infamous
yeah.
emoji.
So yeah, exactly. Yeah, the Fed emoji. So yeah, Yasser, you got a question?
Yes, I have a question. First of all, have you got to see this technique called LoRa adaptation? I guess is the name.
I think I know LoRa, but then it kind of comes under the general umbrella of parameter efficient tuning.
Exactly.
So I think LoRa is like one way where you actually like I might be wrong, but you actually like add like separate parameters to the model, and then you only fine tune that. Here it's like you take that to the input or something like that. I might be wrong, but I think that's what LoRa does.
It's like it's close to what you said. It's very similar to what you just said in the fine tuning part. That in some sense we're not fine tuning the entire model, and we're just fine tuning some subset or whole number of parameters instead of the entire model. So I was just wondering if you read that, like, how does it compare with this? Because both ideas are super similar, I guess.
They are like I think there was like one tutorial by MNLP that I attended, and that's where I learned about all these techniques. And they basically have this parameter efficient tuning as the broad category, and there are different ways. There's one thing like called adapters. I think LoRa is also an adapter. Then there's one thing where you actually prompt tune, so this comes under that category. There are like others as well. I'm not sure, but they how does it compare to LoRa? I'm not sure. We might have to check. But it might just be the case that because LoRa might use more number of parameters, they then find it suitable to compare against that. I'm not sure, but yeah.
This one's definitely a lot simpler, I guess. And if they're comparable, then there's something that's quite elegant about the fact that you literally just have some kind of extra inputs and optimize for them.
Yes.
I guess they're both trying to achieve the same kind of thing, which is like,
Exactly.
here's a super general thing. We need some very strong regularization to make sure it doesn't like overfit to this tiny data set. How do we inject this regularization? Like super naively, you just do like L2 norm on the weights or something. Obviously, like more advanced stuff, you do LoRa. You freeze the weights and learn a tiny embedding at the beginning. All of them are kind of just trying to make sure that the core stuff stays the same, I guess. Because also when you do matrix decompositions like LoRa does, you're doing a pretty strong regularization because you don't let the matrices change quite so much or something like this. I don't know. I need to think about that a bit more. But I know that when you just train from scratch using tensorization with Tensely and things like this, then by training on the decomposition of the matrix rather than the individual elements, you end up having a pretty strong regularization effect, which obviously prevents overfitting and things like this. Yeah, super interesting. But I guess LoRa seems a bit more like implementationally complicated. I need to go through it a bit more, but just reading through it now, it seems like it's a little bit more involved.
I was planning on doing LoRa in one of the future paper reading stuff, actually.
I think that'll be really interesting.
Yeah, it's really interesting to compare it to prompt tuning, I guess. But thanks. This was super insightful, actually. Thanks.
Oh, thank you. Actually, like Hugging Face, like recently also like came up with this new library called PEFT. I can just like send the link here.
Yeah.
So this is basically where they like implement all of these models, and you can just all of these techniques, and you can just use them readily. So you might find more latest references to the thing that is. I think LoRa is also in there. So again, it comes under that general category of parameter efficient fine tuning, and then there's LoRa, there's prefix tuning, P tuning, all of this stuff. So I'm not sure if there's a paper that compares this, but that would be, I think, interesting to know how these techniques compare to each other, and if we can actually like converge to a single thing. But but I think it depends on the task you're trying to do. Maybe like maybe if the complexity of the task is like much harder, then maybe just modulating using the prompts might not be that expressive. We'll have to actually go inside the model, and that's it. So I think it depends on the task you're trying to do, probably.
I guess again, as you say.
Sorry.
Well, kind of you're saying like where I guess in the cases where the model tuning was better on the smaller model sizes, I guess that's where maybe LoRa shines. And when the model is just really huge already, you can probably get away with kind of optimizing the embedding directly.
Yes, exactly. Probably.
Makes sense. So what are your thoughts on kind of what we're exploring with potentially doing code generation and things like this? Just on a high level, is this kind of fine-tuning something that the code generation literature has explored? Yasser, is it something that you think could be applicable to some of the stuff we're doing? What are your thoughts on that kind of stuff?
We wanted to use LoRa. We were planning to do that. I think everyone now is not like they're trying to go away from the idea of fine-tuning an entire model. If you have a model that's like 13 billion parameters, you really don't want to fine-tune the entire thing. It already has enough knowledge. You just want to fine-tune a subset of the parameters or a smaller number of parameters. So we are aiming to use LoRa or any kind of these parameter efficient techniques.
And starting with a big off-the-shelf kind of code generation model like the ones from Salesforce and things like this, I guess. Yeah. Okay, makes sense.
Cool. I think the new models coming up that are even smaller and perhaps you can like fine-tune them end to end. There's one like Star Coder or something like that. I don't know. They came up recently, but maybe it's I don't know. Like depending on the bandwidth, it might be worth exploring that. If complete fine-tuning can actually learn like IV in general, and then it can, but that might require more compute. So there's a trade-off. I don't know. Like just Oh, it
Makes
was 10 actually. Okay.
So it's also Bao had a question, which is yeah, correct. So
Oh, sorry.
Bao said, isn't this kind of like adding some extra params or layers to the start or end of a frozen NN and then fine-tuning those params layers? For CNNs in vision models, you can add small learnable patch to any input image. Yeah, it pretty much is the same.
It's the same thing. Yeah, it's
exactly.
the same.
Yeah.
In fact, like it's similar to adversarial attacks where you actually learn an input which deliberately gives you the maximum log likely the worst log likelihood, and then you feed it there. Yeah, exactly. So it's very similar to that. Yeah.
Yeah, and yeah, there's lots of areas where kind of small latent space optimization is done. In fact, one from our lab, got this fly keep coming around me. There's a project that called Code Slam, for example, that does the same thing for. It's pretty old now, but came out of the lab I was in and does this for kind of vision, 3D and stuff. But I mean, there's loads of stuff obviously where you basically optimize very low rank, very kind of small latent spaces for various reasons. But yeah, I think this is a really interesting application of that kind of thinking. Yeah, any other questions? Again, I know that there's probably people with varying levels of experience and familiarity with this, so questions, kind of beginner questions or advanced questions or any kind of questions, welcome. So any final questions before we wrap up? No. Okay, well we're good on time. We're exactly on 8:30 or 8:30 my time at least. So yeah, well, thanks again, Jatin. That was super helpful and insightful, and yeah, making me really excited about continuing this. I think it's really good that Yasser gave the push for us to start doing this. It's long overdue for us to start doing some reading groups. So thanks for that nudge. I will very happily do. I'll very happily do. Just something simple like attention is all you need next week, just to make sure we all have the baseline. Again, most people are probably very familiar with it, but there's no harm in getting us all kind of on the same baseline. I also do want to do flash attention, so I'll pick up on some of those next week as well. But then we can get a big queue of people lining up to present all kinds of cool stuff. So yeah, really happy you were able to kick it off, Jatin. Thanks for explaining all that. And yeah, and I hope. Sorry, go ahead.
I think Aditya had a question. I think
I think he was trying to applaud, probably.
I was trying to applaud, but I actually had a question as well.
Oh, you have a question as well?
I'm not sure super relevant, but do you think if so in like a large language model, at least the ones that we use like BARD or GPT, do you think like if I have to like classify something, my prompt will be like, it can be very generic, like tell me distinguish between this, or it won't be like exactly the one that you're trying to replace. So has someone tried to like map these general prompts of like a classification task to like this specific prompt that has been engineered, and then sort of like redirected towards like the better trained model or something of that sort? Like I'm trying to understand like
I guess one thing to clarify is that the optimization isn't normally for a prompt, it's for a task. So so kind of the task is entirely defined by the data set and the training loss pretty much, and the prompt is irrelevant.
My question, like I'm just thinking about how can this be sort of like moved out of this very task specific place where you're just like competing for benchmarks and like more into a very more general space like ChatGPT or
I think meta learning is one really interesting one. Sorry, I know I'm answering a question. Maybe you can answer, Jatin, but if you can imagine like maybe kind of one-shot learning or something where like you meta learn some latent space at the beginning, and then it tries to kind of very quick, and you give it a few examples of like what is a good question and a good answer, and then it very quickly regresses, and you train the whole thing end to end using model agnostic meta learning or something like this, where you have like second order gradients that basically learn an initialization of the latent space that's really, really good at very quickly learning new tasks flexibly. This could be one angle where we could kind of, but in a way, then you're trying to kind of just do what the LLM's done at the beginning in a way, because it's a super general.
Yeah. Exactly. Yeah, that's what I was going to say.
It's a bit kind of, why would you do that if you have this thing that's been trained on huge data anyway? Like, would you get big performance improvements? Maybe. The point is the model, it's like another level of expressivity. Like the level of expressivity at the moment is first order, which is just a single pass through a network. Now your expressivity is like you can do some second order optimization actually, and kind of optimize something a little bit towards what you're asking it, and it can kind of learn on the job. But I don't know if you have any thoughts on how that could become more general and less just like task specific for benchmarks, Jatin.
I'm just thinking, like, why would you like want? Okay, so maybe one thing might be is like instead of like training for each specific task, a separate prompt, you can have just a single prompt. But then I just consider it as a trade-off between like the time and the performance, because the time here is very less. I would just might as well have different things. But this is in context to like I want the best possible performance on this data set. But if I want more general performance,
I guess kind of moving towards, you know, AGI and bigger questions like you don't optimize things for data sets, you optimize it for like general intelligence and stuff. But I think in that case, obviously, just training the model once does very well. If you want a model that can kind of adapt and learn in new situations, then I think kind of meta learning stuff is quite interesting, because then basically as you're asking questions and you say, no, this is wrong, this is right, it can then adapt its latent space based on your supervision of kind of how well it's doing or something like this.
I think meta learning has come so much this presentation. I think we should do a briefing on this.
I've actually presented some of those in my old lab, so I've got some slides hidden away somewhere for kind of reptile and mammal and stuff, so I could present those at some point as well. Guillermo had his question as well.
So just a very specific question maybe, but do you know if there is any study or any paper related to interpretability of these learned vectors? So basically, is there anything that maps the learned vectors to a group of, like, obviously not a specific word, but maybe something near specific words in the the vector space?
Okay, I'm not aware of these studies as such, but if you're looking for like in general interpretability in context of large language models, I think Anthropic's work is like fantastic in interpretability. So I don't know if you guys know Chris Olah. Like he like has a lot of good blogs. So that like the Anthropic lab like just puts out like really amazing papers on interpretability of models in general. So I think that maybe lead you towards that, but I'm not sure in this very specific intent that if there is any paper. But if you're in general looking for interpretability, that's a very good result. Like I actually like that a lot. So you can like read through those.
Sure. Thank you.
I remember Chris Ola's blogs from when he like did the blogs on LSTMs and everything a long time ago. He's got a long history of doing really good explanations.
Exactly. I think now he's spun up an entire lab that does this. Some blogs. Well,
it's a really like important piece of the whole AI landscape to have like really well explained kind of blogs and stuff.
Yeah.
Cool. Any other questions at all from anyone? Okay, well, I guess we can wrap up there. But yeah, again, thanks a lot, Jatin. Really insightful, really helpful. Again, thanks Yasser for giving us a nudge to start doing these. I think having one every week is going to help keep us all on our toes in terms of kind of research awareness and everything like this. So it was really great going through all of that. And yeah, I'll look forward to seeing you guys all again in the next one. Thanks everyone. Hope everyone has a good evening, and see you guys all again soon. Thanks a lot. Bye everyone. Bye.
Bye.